What we are seeing here is not an animation. This is a real-time closed-loop digital twin. A real PLC controls a simulated heat exchanger and continuously reacts to simulated physical feedback generated by the digital twin. Valves open and close, fluid flow, temperature evolve, and every decision comes from the PLC. Before looking at tools or code, let's look at the system. On one side, we have a real PLC running deterministic control logic. On the other side, we have a simulated physical process running in Isaac Sim. The PLC sends commands to the digital twin. The digital twin applies those commands, simulate the physics, and send real-time feedback to the PLC. This closed loop is the foundation. Everything else builds on top of it. Let's start on the PLC side. In any scalable industrial system, control logic must be structured, reusable, and deterministic. For that reason, each valve in this system is implemented using a user-defined function block in FactoryTalk Design Workbench. This function block encapsulates every related to the valve. Automatic and manual modes, open and close commands, status feedback, and alarm handling. The key point is this: we implement the valve logic once. The plan may scale, the control logic does not. This is the strict rule of the architecture. The PLC is the master of all real-time decisions. Now, let's move to the digital twin side inside Isaac Sim. Here, we apply the same discipline. Each valve is represented as a reusable object built with OmniGraph. The object handles animation, visual state, and sensor feedback. When the PLC sends an open command, the digital twin does not decide what to do. It simply applies the command and simulates the physical behavior. This is an important distinction. OOIDT does not introduce new logic. It mirrors the deterministic control architecture in the simulation domain. Because these blocks are reusable, adding a second valve is just duplication. No new logic, no new behavior, no special case. Even the piping animation follows the real control state, showing fluid flow based on actual valve position. Now, let's look at the system in action. The PLC opens valve VA03 hot fluid starts flowing through the exchanger. Inside Isaac Sim, the physical process is simulated in real time and the temperature begins to rise. This temperature is not calculated or fake inside the PLC. It's generated by the simulated physical process measured by a virtual temperature sensor and sent back to the PLC through a Python PyLogic I/O bridge. As the temperature increases, the PLC continuously evaluates the process variable. When a threshold is reached, the PLC reacts. It closes the valve VA03. Nothing here is scripted. The PLC is not following a predefined timeline. It reacts continuously to simulate physical feedback. This is what makes the digital twin credible. At this point, the benefit of the architecture becomes clear. We have one valve logic block on the PLC side and one valve object on digital twin side. Yet we can scale the multiple valves, multiple exchangers, or even entire plant. The same control logic scales in the real system and in the digital twin. That's the difference between a demo and industrial digital twin. This architecture is the foundation. Later, analytics and AI can observe behavior, detect anomalies, and predict maintenance needs. But real-time control always remains deterministic. The PLC stays in charge. This is how scalable real-time digital twins are built. If you are interested in architectural design patterns for industrial digital twins, consider subscribing for the next demonstration.